introduce you. Professor Felipe Llanes Estrada is a professor at University Complutense of Madrid. He obtained his MSc and PhD at North Carolina State University with a Sarah Jefferson Lab Graduate Fellowship. He was a postdoctoral research scholar at Stanford Linear Accelerator Center, at the University of Tübingen, and at the Technical University of Munich. He has visited dozens of international research centers and published numerous scientific papers with international collaborators. His interests span many aspects of particle physics, especially around hadron physics and applications to astrophysics. Felipe, we are glad to have you here at LISHEP. You have 30 minutes for your talk, and please feel free to start.
Thank you very much, Professor Abreu, Professor Santoro, for the invitation. I am honored to give this talk. It would be much nicer to be over there. Something got wrong. But anyway, so here's the thing I committed to, giving an overview of gluonium, although I've seen that in the conference, half a dozen people could do this even better than me. I imagine they can do everything at the same time. So here I am. So a founding myth of our Western world is the travel of Odysseus. And I bring this up because I'm going to use them as tops for what I'm going to be discussing. Why? Because Odysseus only very belatedly reaches Ithaca. Yes? So the story of Glueballs starts probably in 1972 with Fritsch and Gelman, though the first papers that have Glueball in the title that I have found, well, one is from Don Robson, 1977, who was trying to identify a vector Glueball. Good luck to that one. Then Sidney Coleman wrote another saying that there are no classical Glueballs. And then I found 1,500 more and counting. So this is about 75 papers per minute. So you'll forgive me if I have to leave many classical topics out, like, for example, central production was very painful. Won't be talking about that. Yes, so now, here are the islands we're going to visit. What are the Glueballs supposed to be? Understanding a bit the theoretical Glueball spectrum. Well, these two things probably for a fully hadronic physics audience I could skip right away. But I believe there's a mixed audience and some people are working on other things, so I'll cover them. Mixing and decay, some hints from high energy scattering. This is what we really want to talk about today. I imagine you saw Carlos Avila's talk on the other day. And then I'll take for a new paper on extreme kinematics and QCD counting rules. Okay, so that's the plan. So let's start traveling and see what the Glueballs possibly are. Well, you remember quarks, 3 colors, gluons. These are like the photon, the radiation, but they come in 8 kinds. Yeah, quarks came up with flavor. With SU3 combinations for mesons and hadrons, you could pull off the quark model. Then they were shadowed. We consider a shadow with deep inelastic scattering because these structure functions are flat. They don't depend on Q² at fixed x. And then we can see them as back-to-back jets. Yes, very good. Quark confinement is very well tested. For example, there was a repeat in Los Alamos of the Millikan oil drop experiments looking for fractional electric charges. Came out empty-handed, of course, as we would have heard. For example, if you look at DEDX in a tracking chamber, well, you can see the proton, the kaon, the pion, whatever. Well, somewhere here should be the strange quark, and there's nothing. Somewhere here should be the light quark, and yeah, there's nothing. Okay, and dedicated searches were made, and quarks were not found. So we think we understand that they're confined because of the color interaction. Now, gluons are seen in jets too. Here are 3 jets. This is a Tasso event that basically discovered the gluon, right? 2 quarks and the gluon coming back to back. And then the thing that's not so well tested is gluon confinement, right? So if gluons came out of the proton in a collision, they would hit the secondary, they would hit the target or the TPC or whatever and eject secondary protons. They would appear as some thick neutrons, right? Their interaction cross-section would be a bit bigger than a neutron, something like 3 barn. I tried to estimate once. And this has not been studied a lot, but no one has seen really, they haven't been searched so much for, but no one really has seen like thick neutrons hitting material. So we take it that gluons are also confined, and what makes sense is color confinement. Okay, Very good. Are gluons massless? Well, if you take the Procca equation for a spin-1 particle, this term is not gauge invariant. Yeah, so we have to cross it out, and then we cannot accept a mass. Very good. However, the hadron spectrum is discrete. You know, for example, here is the charmonium spectrum. You have a few discrete levels. Here is a flavor nonet, and these are very well separated levels, you know, pion, kaon, eta, eta prime. There's not a real continuum of them, okay? Now, if gluons were really massless, you could just add 6 gluons to the pion and form another mass, another state with the same mass as the pion, but with any quantum numbers you wanted, basically. You just give me your quantum numbers, and the hadron spectrum would just be very, very filled, okay? So somehow this has to appear dynamically, all right? So, for example, you can use a Higgs-like mechanism or like a plasma mechanism in which a dispersion relation will be k squared plus mg squared, or you could use a cavity-like back model type of dispersion relation satisfying such a gap equation, or you could use Gribov's confinement type dispersion relation in which the mass would actually diverge at low k squared. Well, anyway, I used the gap equation of Szczepaniak, Swanson, G, and Kotange, which looks like this. You have a dispersion relation which would be just omega equal k if there were no interactions, but then it picks up some interactions, and this gives you a dynamical dispersion relation that looks like this. So there's similar things from the quark and the anti-quark, and this will be the gluon dispersion relation. So up here, the mass is essentially 0. You just get energy equals k. That's when you see high energy events. And down here is when you see actually hadrons. And the degrees of freedom are gapped, and that's why the hybrid mesons that Cardis-Meyer was showing are so far up, okay? Now, are there states made of pure glue? Well, Maxwell's equations are linear in vacuum, all right? So we don't expect classical bound states of radiation in vacuum. In QED, the photon-photon interaction is very weak. This is the Euler-Heisenberg-Lagrangian. It's alpha square, and it's non-resonant. It's just a very perturbative thing. Well, gravitons remain to be seen, so I'm not going to talk about them. So glueballs might be the only pure radiation composite state that we have at hand, except we have been looking for them for 40 years, so they're still at hand. Anyway, and we consider color singlet glueballs only, yes, because of color confinement. A typical lattice QCD computation would construct some operator, for example here a plaquette, and would let it propagate forward in time. Now, this is Euclidean time. You have to convert to IT. And so e to the IHT, which is the evolution operator, becomes e to the minus m times the Euclidean time. So in the lattice, they're looking for exponential things that fall. And then when they get rid of several states, well, they look for a plateau where they have the ground state, and they kind of try to fit there what m might be, okay? And that's how the calculation is, and it's a Monte Carlo. All right, let's stop at the next Thailand. You can see the wanderlust that we all have after all these months tied up, right? So let's go to the theoretical glueable spectrum. We see how the lattice calculates it. So what do they get? Well, this was the status in 1995, 25 years pass. This is how it looks in 2020. The boxes here were the actual spectrum back then. Yes, the lines are the North Carolina model. Now the lines here are the lattice spectrum now. So what these people achieve is a tremendous reduction of systematic error, okay? So this is the takeaway point here. And also, I drew the charmonium band. So above here, you have charm states, charmonium states. And below here, there are 4 glueballs that can be looked for in the light quark sector. Okay, this hasn't changed much. Maybe the ordering, here it wasn't clear. Now it appears that the 2++ is a bit lighter than the pseudoscalar. All right, so there's progress. And of course, there are older papers from the 80s that I'm not quoting anymore. Fernandez is in my faculty here in Madrid. Anyway, the best known spectrum is this one by Morningstar and Perdom. And we see here same features, 0++, 2++, 0 plus. Yeah, are the lightest one. I want you to focus on this 3 state that will come later in the discussion, and that's above 4 GeV, okay? This is at about 4.2 GeV plus minus 200 MeV nowadays in the lattice, in more modern lattice calculations than this, but that's where it is, okay? Already Morningstar and Perdom had it about 4 GeV. Anyway, the lowest lying states have all charge conjugation plus, and none of them has J equal 1, yeah, in this cloud here. The first J equal 1 appears around 3 GeV. Very good. Bit of a closer look to a more modern spectrum. This is at another O and Tepper. And well, I was kind of going to say here that these four glueballs might be kind of discrete in pure Yang-Mills theory, but of course they're not discrete anymore when they mix with quarks. But if you go above 3 GeV, you open the two glueball spectrum. So even within Yang-Mills theory, these things can decay to two glueballs, right? So the number of things that are kind of discrete is not so large. Yeah? You have this huge spectrum with many possible states, but there are not so many that actually can be searched for. Yes. Anyway, what is the back of the envelope estimate for the mass? Let's see. Let's take a baby model of the proton as a quark and the diquark. So here I put two quarks together. So this quark is a color triplet, and this diquark is an anti-triplet, right? So it's like a meson. So then the string tension is 4/3 of sigma. Yes, it's something that we know. We can pull off the color factor, and it's 4/3. Now take two gluons, two of these constituent gluons of the picture I showed before with the mass cap. Well, now the string tension is 3 because they have more color. They're in an octet representation, right? They're stronger in color. Right, so the string tension is different. So now imagine that a lot of the mass comes from a flux tube forming around these things, okay? Well, then you would expect the mass to scale as the color factor, right? So it's 4/3 over 3, which is 0.44. So you would expect the proton to have a mass of about 0.44 times the mass of the glue ball. And that, you put the 900 MeV of the proton, and then you get something like 2 GeV. So that's okay. That's what we expect glue balls. Well, if you look at very old papers in the 80s and before, you would see claims of 800 MeV and things like that. Don't think that's very tenable nowadays, especially with the lattice computations. Okay, very good. What else can this constituent model tells us about the quantum numbers of two gluons? Eu preparei este slide a última vez que o Brasil ganhou a Copa do Mundo. Sorry, talking to myself. This is a very old slide. We have here two gluons and the Clebsch-Cordan cupping the spins, and then a spherical harmonic, and then you can get 0, 1, and 2 ++ with 0 angular momentum, right? And then with L = 1, you can get 0, 1, 2, and 3 -+. But wait, 1 is out. You cannot form the angular quantum numbers 1 ++ or 1 anything with two gluons because of Young's theorem, right? You have two spin 1 particles, say photons or gluons. If they are transverse, well, they are in my work because I use Coulomb gauge, so K.A is 0, and they're bosons, right? So Young's theorem states that they cannot couple to spin 1. That's right. That's how we knew, for example, that the Higgs cannot decay to two photons if it had spin 1. So it was ruled out immediately for the high energy folks. Okay. This is automatic in Coulomb gauge QCD modeling. In other approaches, it becomes a dynamical question that you need to sort out why the lattice low-lying states are at 0 and 2 and not 1. Okay, this is natural in Coulomb gauge. Anyway, so what are these glue balls? Let's go to the next diagram. Well, quantum number filters are very common to get at the F0 and F2 spectrum. So if you look at J psi to vector meson, then because the vector meson, say a phi or an omega, takes the quantum numbers of the J psi, what's left is in a ++ parity charge conjugation state, and you can see the F0 and F2 spectra. So here you see the sigma. This was a beautiful discovery of the sigma when they did this with a photon instead of a vector meson. And we have here the F2 1270, and well, we're interested in things a bit higher up, given how the lattice data is coming. So this F0 1710 seen into kaons, and then also the 1500 will come up in the discussion somewhere here. Yeah. So this spectra of vector pion or vector kaon are a beautiful filter. Okay, so that's how basically we know what states populate this area. So then we have to look at mixing. The classic evaluation here is by Amsler and Close that came up with the idea that F0 1500 would be the glue ball, but then mixing centrifugated it to F0 and F0 1370 and 1710. Well, how do these calculations go about? These things are taken as point-like particles. We don't read their structure. And so you take just a flavor analysis. Glue ball to pi, you take as reference 1. Glue ball to kk bar, well, that's r. If flavor symmetry is exact, this would be 1. And then eta and eta prime are given by Gelman's flavor. And you can read the coefficients of. And then you can see with the data on hand, yeah, how much the F0 1370, which is the inner circle here, how much the F0 1500, which is the middle circle, and how much the F0 1710, which is the circle, have of light quarks, that's blue, orange is for strange quarks, and the gluons are the green thing here. Yes, it's very little green. So in this analysis, this is by Jacosa, well, the little green band is the glue ball. So the F0 1710 is almost nothing. It's mostly on the F0 1500, okay? And here's another analysis, slightly different, similar conclusion. You have the light quarks mostly on the inner circumference, and you have the glue ball on the middle one. Okay, and everything is mixed, basically. Now, more modern analysis, here the extra information is dynamical. Jacosa and company, what they did here is assume that the glue ball has to do with dilatations. So they put some elements from a dilaton Lagrangian. Well, then they can get the F0 1710 to be mostly the glue ball, and the F0 1370 to be quark anti-quark, and then the F0 1500 to be more strange. Okay. Anyway, so what exactly are we mixing? Well, these flavor components that are usually meant in this analysis are just fields. They're like point-like things. Some singlets, some octets coming from quark anti-quark or whatever, and then a surplus, which is the glue ball. Yes. You can put some extra dynamics, like it comes from dilatation symmetry or whatever, but it's done at the point-like meson level. Now we would like the full answer at the quark and gluon level, and then things get stickier because if you write a Fock space expansion, this is gauge and scale dependence. Well, you can take a low scale and take Coulomb gauge, and then you're home free. You can say what's a quark anti-quark, what's a glue ball, you know, what's a free gluon glue ball. But then, of course, if you go to light from gauge at a higher scale, you need to convert. Okay. Well, a way to do it in the lattice maybe is to check the relative signal given by different interpolating operators. All right. Finally, I wanted to comment on large NC counting. Now, large NC doesn't give such a full answer as the Fock space expansion in some gauge. But it's scale and gauge independent. You know, it's ambiguous in some sense. For example, hybrid mesons and conventional mesons both have widths of order 1 over NC. We cannot distinguish them from large NC. But glue balls actually are narrow. Yeah? In large NC, the glue ball component of anything has mass of order 1, and then the width is suppressed as 1 over NC squared. So in a world of large NC, glue balls become decoupled very quickly. We don't expect them to be very broad mesons. Anyway, is this naive flavor SU3 thing that people use a good guide to put the glue ball as a singlet? Right. Well, there was this paper by Chanowitz showing that in all orders in perturbation theory, the mixing with QQ bar is suppressed for zero quark mass. Okay. That means, in short, that the 0++ glue ball, if you have only chiral couplings, cannot go to a 0++ quark-conium. You cannot mix these two things. Right. And now this makes the width to KK bar larger than the mix to pi pi. Yes, so the glue ball is not such a good singlet after all in these works. Well, Albaladejo and Oyer quantify this. They find that F0 1710 to KK bar is true. And using these ideas of Chanowitz, they fit it and find that this is largely the glue ball, the extra singlet. Yeah. Now we have to take into account that chiral symmetry is spontaneously broken beyond perturbation theory, right? So then you have spin orbit interactions that are non-perturbative, and then this argument weakens a bit. Okay. Anyway, lattice, I was told in a workshop yesterday, is now suggesting very large mixing in the low spectrum. This is a computation from Brett. The low-lying spectrum has been computed in the same lattice with and without quarks. And, you know, the low and the middle spectrum looks very similar. Yeah, so they interpret this as mixing being large. All right, no pure glue ball is standing out of this spectrum. Evidence pointing to the F0 1710. Additional evidence, well, we have the radiative decays. I show the meson decays, but you can also change the vector meson for a photon. And then computations give you an expectation for photon plus glue ball at the order of 4 10 to the -3, even larger for the tensor glue ball. And this is consistent with best 3 data for this 1710. They see 10 times more 1710 than 1500. Okay? And then Eberhard Klemmt has done another flavor analysis and found that F0 1500 is octet-like. This is based on CERN data. That F0 1370 and F0 1500 are mixed, like NN bar minus SS bar and NN bar plus SS bar. So this is light minus strange, light plus strange, which is far from ideal. There's a lot of singlet octet mixing here. And therefore, he assigns also the 1710 a bit more to be a glue ball, perhaps. But in their latest work with Sarantsev, in this article here, they have used each of the mesons as pseudodata. So they have separated the octet-like mesons, which are these red ones, and the singlet-like mesons that are these blue ones, and they looked at the J-psi decay rate, okay? So this is pseudodata. So each one of these is one meson in this plot, and they look at the mass. And then they think of the glue ball as the broad structure underlying the singlet, right? They call this a fragmented glue ball. It's a glue ball that's divided among all these mesons, okay? And they say that it comes out with an 1865 mass and a 1370 plus minus 50 MEV width. That's a broad meson. It's normal. It's like any meson in this mass range. But as I said, the width and the mixing are suppressed in large NC. We expect the glue balls to be narrower, so I don't know what to make of that. Lattice computations, these are quaint still, give something like 100 MeV width. The Coulomb gauge gluons give like 100 MeV width. Some rules, however, which I'm going to flash a slide next, give a bit more like 200, okay? What are the mesons in this area like? Well, you have the 1370 that is broad, the 1500 and the 1710 that are kind of narrow, or the 100 MeV, so these are good candidates, and then the 220, which is a bit broader. Anyway, how does the sum rule calculation go? Well, you take a correlator of two currents, say two scalar currents, take the matrix element, take the Fourier transform, and that's a function of the momentum square. The imaginary part, you can calculate at high S in PQCD, and at low S, you approximate with the resonances that you see, okay? So you have some fitable strength constants, and then one of them is the glue ball, and that's how you can get an idea of the width from the fitting parameters of this formula. All right, how about exotic quantum numbers to finish this island? Well, this is a fruitful strategy to search for other types of non-QQ bar mesons, as Meyer was showing. However, we have no flavor exotics here. Yeah, so the late CB push cannot help with glue balls because they're always singlet. But JPC exotics are possible. Yeah, so you can have 0 minus minus, 1 minus plus, etc. Except typically they lie at very high masses, 4 GeV or above. So this is not promising. Here are the sum rules estimates for these exotic mesons, some of them, and you can see that they're way above of the Charmonian line. So they're mixed with a ton of things, right? So it's not very promising to look for glue balls with exotic quantum numbers. Anyway, next move to the next island, which is the core of this physics these days, which are the hints for high energy scattering. I have to remind some of the people here what radio trajectories are. Now take the hydrogen atom, and it will have a Schrodinger equation with a radial part, potential and kinetic energy, and an angular part that has L and L plus 1, right? This is the kinetic part from the angular sector, all right? Now, what are the eigenstates? Well, here you have 1s, 2s, 2p, 3s, 3p, 3d, and so forth, well-known hydrogen spectrum. Now, if you continue analytically this cell to the complex plane, you make L a continuous variable, you can still solve the Schrodinger equation, right? And you can get states that interpolate between 1s and 2p. If you make this a continuous variable, then you have a continuum of state. Well, these things are called radio trajectories. This is the ground state radio trajectory. This is the excited radio trajectory, and so forth, okay? And these are trajectories, angular momentum as function of the energy. Now, because we want L of E, we want to plot this on the other side. So let me flip the slide. And that's how the radio trajectory looks in L of the energy. It's a thing that falls like that towards the origin, okay? So the energy grows to the right, and the angular momentum grows to the top. And that's the radio trajectory of the hydrogen atom. Now, in relativistic theory, the energy goes to Mandelstam S. So this is the energy square. And here comes the insight of Chu and Frautschi, which is very old, which is that if you plot the angular momentum against M squared, hadrons follow parallel linear radio trajectories. So you can put 2 of 3 hadrons of a family, like here the row 3 and the row 5 in a line. And you can do this with several families of well-known mesons and baryons, and they follow straight lines. And well, a straight line with 2 points is not a lot, a straight line with 3 points is a bit, but when you have many of them and they fall parallel to each other, then you learn something. These hadrons are rotating strings with J prime proportional to the inverse of the string tension, okay? Very good. Now let's go from spectroscopy to high energy soft scattering. So we prolong not only L, but also S. We continue analytically the energy here to the left. And then this area is physical scattering with negative T. So this is negative T, this is positive T, where T becomes S, and these things are resonances in the S channel, yes? Now, amplitudes here behave as S to the J power, and J is this J of tail line, okay? Why is this? Well, it's a long story. You can find talks on the web, but basically it's because the amplitude is proportional to a Legendre polynomial, and this is proportional to its argument to the L power, okay? So the amplitude becomes S when you cross to J, to the J power. And the cross-section, of course, has one less index here, so it's J minus 1. This is a consequence of crossing symmetry and causality. So you can prolong these trajectories down here and see how an amplitude behaves at large energy and small t, okay? Before this gets unwieldy, it's too far from the resonances. Anyway, so people did this in the 60s and 70s, and they found that cross-sections, charge exchange reactions, expose the effect of these meson-Rayet trajectories, and as S increases here towards the bottom, if you can get close to the screen and see the energies, the cross-section falls, because it's this 1/2 minus 1. 1/2 is this point where these trajectories cross the origin, and then you have to subtract 1. And so the Rayet trajectories for charge exchange reactions fall. Very good. So what would artificial intelligence trained with this hadron spectrum predict? Hadron cross-sections fall with energy, okay? This is what I would predict too if I had seen that data. Except that's not what they do. Total cross-section for proton-proton scattering becomes flat at high energy, and then eventually slightly grows with a logarithm, okay? So J, the intercept of these Rayet trajectories, has to be about 1. To make a 0 here, you need a 1 in J. All right, so that's the Pomeron-Rayet trajectory everybody talks about, yes? It's a trajectory that, well, here is with some Hera data, that if you extrapolate it to the right side, has a smaller slope than the usual Rayet trajectories, and it cuts the S equals 0 axis higher up at J equals 1. Well, people take 1 plus epsilon, where epsilon has to go to 0 eventually, and the slope fitted to data is something like 0.25 GeV to the minus 2. Okay, so as of 1977, Collins still wrote, "It is clearly rather unsatisfactory that we have been forced to invent this trajectory, which does not seem to have any particles lying on it." Okay, right. So Simonov and company, and maybe some people earlier, this is the earliest paper I could track from 1990, came up with the idea that Glueballs actually fall on this Pomeron trajectory. So this is my own take. That's the Pomeron-Rayet trajectory on the right side of the Chufrauchi plot, and the 2++ Glueball falls on it. And the scalar Glueball we talked about earlier is down here in a dotted trajectory that does not dominate scattering, right? So in this picture is proton-proton scattering at high energy and many other processes without quantum number exchange are exchanging the 2++ Glueball, and then a 4++ Glueball, and then a 6++ Glueball, if such thing exists, all projected down here, okay? Now, what's the slope? Well, Casimir color counting takes you a part of the way there. If you do this 4/3 over 3 trick from before, the slope comes to be 0.44, which is not bad. The ratio of the slope of the Pomeron to the region is 0.28, so it's not too far. And then the rest of the difference must be dynamical. You need some detail there, and computations in the lattice predict this to be something like 1 plus 0.25, which is not too far from 0.28 times t, okay? Anyway, so let me clean the slide and put again the Glueballs and the Pomeron. This is the latest Pomeron from Donaghy and Lanzhou from 2013. This is the older one. And it kind of passes by the 2++ Glueball in the lattice, and then the data would sit here, right? How about odd exchange? Well, this is the new thing. The Oderon-Rayet trajectory with C-1 passes by like 3 minus minus, 5 minus minus here. And I calculated this a long while back, and there are lattice computations also here. And you can see that the actual Oderon trajectory that we need are these red dots, okay? That's what we need if the Oderon is going to make a contribution similar to the Pomeron, yes? Well, computations would project to a band down here, which is very well below 1. In fact, it's below the omega trajectory. This purple line here is the omega trajectory, which would dominate C-1 scattering, as we predicted about 10 years ago, okay, in 2007. So now The claim from
5 minutes, Felipe, please.
thank you. The claim from Totem and PP bar at the zero, this comparison, well, it shows that we actually need a moderum with J at 0 close to 1. Okay, this is a evidence claim. You have seen this talk by Carlos Avila. Please look for it later. I'm not going to go into it. I'm going to talk about the consequences of what this is. Well, if there is a moderum, then the 3 minus glue ball goes down in mass. It has to be mixed or whatever, or the calculations have to come down at 3.5 GeV. And this is something between the J psi and the psi prime, which is a great job for Panda. This is a 3 minus state, which is in the Charmonian region, in a region that's very well accessible. Okay, our predictions tended to be above 4 GeV in the early 2000s. Okay, so what can be wrong with the theory? Well, maybe analytical continuation in J is out. This was never fully proven in relativistic theory, but it's consistent with the corpus of what's known in hadron physics. Okay, did anybody make a mistake? Are the trajectories very nonlinear? Well, several groups have checked this. Newly, also holographic models are coming out that are consistent with what we knew. We have to lower the mass with additional theory. Maybe the uncertainty is underestimated. That's not impossible. I guess that's the first possibility for everybody. Is there new physics? Well, I wouldn't expect it. This is very large energy, but very small momentum transfer. Is the experimental significance large enough? Well, that's another question I'm not best qualified to answer. I've seen a couple of preprints on the web, for example, by this group, Logunov and company, where they fit the total cross-section of proton, proton, and proton antiproton with the oderon and without the oderon, okay? And both fits do a very good job. The chi-square is here, 1.37, 1.53, they're equivalent fits. So, yeah, so a total cross-section that does not seem to be giving very strong, and this is the ratio of the imaginary to the real part, and so they can fit both these things. What I haven't seen is someone fitting the latest Totem result with the Totem D0 result with the t-dependence, okay? So anyway, I don't know what the status here is. Let's move to the last island. That's a new idea. Go to a very large SNT domain at very large momentum transfer and try to separate Glueballs from QQ bars there, okay? So this is based on the Brodsky-Farrar counting rules. The cross-section per unit T goes as a function that does not depend on energy, divided by the energy to some known power. So this is S to the number of constituents in the initial and final states. These are the point-like constituents of the initial and final states, minus 2. Okay, you can derive this easily, either with Feynman diagrams or with currents. Now, if you have arbitrary angular momentum, then you add this here. Okay, there is an additional L. This is for S waves. That's a rule everybody knows. With angular momentum, is slightly generalized. Now, an ordinary QQ bar meson has Ni equals, well, I'm thinking of electron-positron collisions, so Ni is 2, electron-positron, and then the number of final particles minus 2 with 2 ordinary QQ bar mesons would be 2. But if you want a glue ball with positive parity, then you need L equals 1. However, if you do it with gluonium, NF is also 4, so NF minus 2 is 2, but no L is equal to 0. This means that there is a difference here. QQ bar, L equal 1, gluonium, L equals 0. So gluonium has a cross-section that falls slower, right? So the glue ball production falls the slowest. If you make more complicated things like hybrid tetraquarks, they fall faster, okay? So here's the suggestion for Bell 2. You take electron-positron and produce phi F0. The phi tracks the quantum numbers, and it's a very nice QQ bar tag. And the F0 will be either the quarkonium or the gluonium, various F0 candidates or F2s. So take data up to points, say 9 and 11 GeV, and compare the cross-sections and see how they fall, right? So the glue ball is the one of these mesons that falls the slowest. So here is again the spectrum of J psi to photon Fj. Okay, so you have several peaks with F0s and F2s, and one of these maybe is the glue ball. All right, so take it to Bell and see how this falls. S cube, S4, S to the 5. You have a null test, because if the F02s are point-like, you're not seeing anything from quantum chromodynamics. They're just point-like mesons. Then the section falls as 1 over S. Okay, so let's see how these things fall. So suppose in this plot that the gluonium is the 1710. Then this would be the spectrum at 9 GeV square, and this would be the spectrum at 11 GeV square. So this would fall the least relatively, and this would be the QQ bars more suppressed. Okay, that's the idea. All right. One last slide, if I have a minute, for the pseudoscalar glue ball. I barely talked about that one. Here the logic reverses. The glue ball drops off more quickly because it's the P wave. Here the QQ bars are the S wave. Okay, these are all eta-like states that decay like ordinary etas, so they're neutral and they're tricky to catch. But anyway, if you can efficiently reconstruct them, say in Bell, well, then the one that falls faster is the glue ball in this case. Okay, except now it mixes with hybrids and tetraquarks that also fall faster, right? So it's not so easy. And J-psi to photon meson does not work either because it selects positive parity in the first round. So it's still interesting because the mixing with eta and eta prime appears in the anomalous axial current. For example, the anomaly here in the axial current depends on the mixing of this eta prime with the glue ball. Okay, so this pseudoscalar glue ball is very low lying, it's below charmonium, and it's a job for Panda for photon-photon collisions. Maybe this is something that can still be looked at Jefferson Lab, maybe with a polarized source where you can separate the vector from the pseudoscalar annihilation here, at least enrich the sample in the pseudoscalar annihilation, one can make progress. Anyway, to conclude, the glue balls below the J-psi have these quantum numbers. This, I think, is undisputed, 0++, 2++, 0 -+, and we understand very well why and what's the mass scale. 40 years of global searches have not bring an undisputed one, which is bad. There is some preference for F0 1710, but the thing goes on forever. The discussion goes on. The recent claim citing of the Oderon is not what I would have asked for. It's a bit at odds with mass predictions from theory. Of course, in 10 years, if this data is established, we'll have to do some soul searching and see how the prediction of the 3 global has to come down. The PQCD counting rules are suggesting that when S is proportional to T, you can select the positive parity globals over the quarkonium. Well, I'm sure there are many islands left before we reach Ithaca in this study, and I'm young enough that I hope to see a lot of progress. And I want to thank again the organizers for hosting us.